Today we'll be testing the efficiency of an AC-DC converter, the TDK Lambda DRB50 24 volt 2.1 amp DC power supply. It features a 100 to 240 volt AC input, and we will be loading it with this resistor load box here. We will be monitoring the input power with the Newton's fourth single phase breakout box, which will be taking the voltage and the current to channel 1 of the power analyzer. The output power will be broken out of this load box, and we'll be monitoring the DC voltage and the DC current with channel 2 on the power analyzer. The power analyzer we'll be using today is the PPA1530, which is in fact a 3-phase analyzer, but it's also available in 2-phase, a 1520. Even though we have the 1530 today, what we can do is set the instrument up and disable the 3rd channel, monitor the input power, as I said, on channel 1 and the output on channel 2, and then what we can do is on screen, real time, compare the 2 powers and provide an efficiency measurement on screen as a percentage. We'll be testing 2 load points, approximately half load and full load. So let's turn the power analyzer on, and we will connect the fan. The fan is just for cooling of the resistor bank. It's a very simple load that we're using today, and we're going to connect the DC supply, and as you'll see, green light, the DC is okay. The power analyzer is currently in default configuration, and what we're going to do now is set up the device to measure the input power on channel 1 and the output power on channel 2. Now, important points to remember today is we have AC 50 Hz on channel 1 and we're going to have DC on channel 2, and as with any power measurement, we must ensure that we are synchronized correctly to the frequency. Now, what that means is we're going to have to separate the 2 channels with regards to frequency detection. This is due to the fact that the frequencies are different, and we want to ensure that each channel is optimized upon its individual measurement. The PPA 1500 can do this, and if we go into the acquisition menu, we will change the wiring configuration to single phase 1 plus phase 2. In the N4L power analyzers, always consider plus, meaning separate frequency detection. So press enter, enter again, and then what we can see is if we look at channel 1, we have 247 volts, 26 milliamps, this is in standby, and we've got 209 milliwatts there, and the 50 Hz is synchronized correctly. Now, if we go to channel 2, what we can see is we have got the correct frequency. This is off load. Let's just put it on load. So 23 watts there. Now, as we can see, the analyzer is showing 0 Hz, and that's correct. However, on occasion, if you have a noisy power supply, so if the filtering isn't quite as good as this TDK power supply, then you may see the frequency start to try to detect maybe the switching frequency of the switch mode power supply. Although today that's not happening, we want to ensure that the power analyzer does not attempt to lock onto that frequency. A simple setting, if we go into the coupling menu, once we've set individual phase 1 and 2, so remember the plus, we can see that the phase 2 coupling is there now, not just coupling. So we've got separate coupling options for each channel. Let's put that to DC and hit enter. Now, although we're DC coupled, that's purely a frequency detection option, not bandwidth limitation. So you will still achieve the full 1 MHz bandwidth of the instrument. So let's have a quick look on the oscilloscope. We can see DC on channel 2, phase 2, and we can see a typical switch mode power supply rectifier input on channel 1 with the sinusoidal wave from the UK mains that we're monitoring today. If we go back to power, what we can also do is enable efficiency now. So if I press the mode button, I can then scroll down to last line. I'm not interested in monitoring VARs today, so what I'm going to do is I'm going to swap that for efficiency. Efficiency, enable efficiency. Now I want to display my efficiency on the phase 1 column, so that means I want to be calculating the next phase, which is phase 2, the output power, over the input power, the current phase. So next phase over phase is the correct answer there. So as you can see, on channel 1 now, we are showing 87.45% efficiency. So we've got 26 watts on channel 1, 23.1 watts on channel 2. So if we then want to only display the input power and the output power on screen, what we can do is if I scroll through again, I've got a view with all parameters there, phase 1 and phase 2. Of course, more parameters are available via software, and you can log up to 60 parameters at a time via software. But today we're looking at just on screen what we can do on the display. So if I press the zoom button now, continue to press it until you can see just the red boxes around the items on screen. Press the delete button and it deletes all the zoomed parameters, and we can start again. So I want to monitor the input power, the output power and the efficiency. If I press zoom, it zooms them in once. If I press zoom again, it zooms them in twice. So in zoom 2 we can see we've got input power, output power and efficiency on screen. What I'm going to expect now is, as I load the device up to full rating, we'll expect the efficiency to increase slightly. So let's do that. Excellent. So as expected, the 89% there, slight improvement on efficiency with 50 watts in and 46 watts out there. So the device is performing as expected. If I just zoom out once, and then we can see that we've got 0 Hz, 50 Hz, 24 volts as expected, around about 2 amps, so we're nearly at full rating, 1.915 amps, 400.9 milliamps and 247 volts. So this was efficiency measurement of AC-DC converters. The PPA1530 can equivalently perform just as well on DC-DC converters, so you can achieve real-time measurement of a DC-DC converter and obtain the efficiency of the devices. We can also monitor AC to AC converters, so if you have a frequency converter, we can monitor the AC efficiency of the device and so on. Thank you for watching, and we'll see you next time.